Today, in this video right here, what I'm going to talk about is how to calculate the molar solubility of a salt in a solution, but then also do a few calculations to highlight the common ion effect. So if you already have one of the ions in solution that actually affects the solubility of whatever it is that you are trying to dissolve in those cases, and we'll be able to see that by actually being able to calculate out what the molar solubility then is of the salt in those cases. So the way that we approach these problems, right here, it says calculate the solubility of lead iodide in moles per liter in grams per liter, and then calculate the molar solubility of lead iodide in a 0.10 molar solution of lead nitrate and in a 0.01 molar solution of sodium iodide. So we're given the KSP, right? We're given the solubility product of lead iodide, so that's 1.4 times 10 to the 8. So the first approach that we should do for any of these solubility, just like with any kind of equilibrium reaction, right, is first writing out what the reaction actually is. So we have solid lead iodide, and so that gets dissolved, and it forms lead 2 plus 2 equivalents of iodide ion, and both of these are going to be aqueous. Right, so that right there's our reaction, and so that's our KSP in this case is going to be that reaction right there. So 1.4 times 10 to the negative 8. Now we can write out what the expression is for that equilibrium. So we have the concentration of 2 plus is going to be part of it, and then we also have the concentration of iodide squared, right? Because there's you get 2 iodides out of that reaction. In this case. So we have this part right here. So all we have to do now is we can just, set up an ice table to make ourselves comfortable in the matter, right? So we have an ice table. So the solids don't contribute, so we don't have to worry about those. Starting off, right, we're going to have 0 of both the lead and the iodide because it hasn't dissolved yet. And so we're going to be gaining X of the lead 2 plus, and we're then going to be gaining 2X of the iodide ion in this case. And so at the end, right, we should have X of the lead 2 plus and then 2X of the iodine ion, right? So now we can take that and we can throw that into our KSP expression that we have over here. So right, we throw that in right here. So we have X is the concentration of lead 2 plus, and then we have 2X as the concentration of iodide, and then that's going to be squared, right? So that's a very important thing to not forget, is that one, it has to be 2X is the concentration for the iodide in this case, but also that you're going to be squaring it. So we take that and we work our way through it, and so what we get then is 4x to the power of 3, right? So 4x cubed. So we have 4x cubed. We take that, we solve for x in this case, and so what we get is 1.52 times 10 to the negative 3 moles per liter, right? And so that's the molar solubility of lead iodide. Now, to calculate then the solubility in grams per liter, all we have to do is just multiply it by the molecular weight, right? So the molecular weight of lead iodide is 461.01 grams per mole, right? And so if we multiply our solubility, our molar solubility, by that value right there, right, the moles are going to cancel out and we'll end up with grams per liter. So if we do that, in this case, what we get is a value of 0.701 grams per liter, right? And that's the solubility of lead iodide, right? It's not very soluble. If you have a liter of water, you can't, you throw a gram in, you're still going to have some of the solid left over, right? So it's not a super soluble. It's not soluble at all, really, in my opinion, right? That's a pretty small amount. So that's just the basic one for lead iodide. Now, if we wanted to do it then for the common ion, right, where we're already having some of the ions present in solution, all we have to do now is just simply do an ice table, but just simply our initial conditions are different, right? So if we go and we do the PbNO3 scenario, right, where we have the lead nitrate, and so this right here, right, that concentration in this case is going to be 0.10 molarity in that case. And so if that breaks down, right, you're going to then end up with 0.10 moles of lead 2 plus in this case, right? That breaks down to, in that case right there, right? And so that's going to be our starting conditions for the lead 2 plus when we're trying to dissolve our lead iodide. So now again, right, lead iodide solid doesn't contribute. Pb2 plus in this case, right, starts off now at 1.01 molarity, right? We don't have any iodide in solution, so that's going to be 0. Now, again, the thing to think about is that the equilibrium for any kind of solubility thing is always going to be going towards the right? You're always going to be adding more into the solution. It's not going to ever be a negative X for a solubility product unless you're looking at an overall equilibrium that's also going to be, the addition of something else. And those become a little bit more tricky to work out. But if you're just simply adding more of one salt into something that already contains some of that salt, you can kind of calculate how much more of that salt is going to be dissolving. So in this case right here, right, the change is going to still be plus X. The change for the iodide is still going to be plus 2X. And so at the end, we should have 1.01 molarity of lead 2 plus in solution. And then in the case of the iodide, right, we should then have now 2X as the concentration in solution. And so we go through, right, is the same thing as what we had done before, right, where we have KSP. And so we have, the concentration of the lead iodide times the concentration, the concentration of the lead 2 plus times the concentration of the iodide ion squared. And so now we plug in our numbers that we have here. So we have 0.10 molar plus X as our concentration for the lead. And then we have 2X squared as the overall expression for the iodide. And so if we work our way through that right there, what we then get is the expression 0.40 x squared plus 4x cubed. And so that's then going to be equal to the solubility product, which is 1.4 times 10 to the negative 8, right? And so now we can easily just simply solve that, right, for x using algebra again. And so we do that, and what we get is that the molar solubility product is 1.87 times 10 to the negative 4 moles per liter, right? And so comparing that to what we had for the lead iodide on its own, we can see then that we've gone about an order of magnitude lower in solubility by just having already a solution of 0.1 molarity lead 2 plus present. Now, the other example that we have that we're going to work through is now we already have a solution of sodium iodide that's present. So sodium iodide, the concentration is 0.10 molarity, right? And so if the sodium iodide is dissolved, right, it's going to break up into 1 moles of sodium, 1 moles of iodide, or one equivalent in those cases. And so we can just simply say here that the concentration of iodide that's going to be present already in the solution at the beginning is going to be 0.010 molarity solution of iodide that's present. So we set up our ice table again. So once again, right, lead iodide solid doesn't contribute. So now, right, we're not starting off with any lead 2 plus in solution. We're starting off now with iodide in solution. So that's going to start off with a concentration of 0.10 molarity. The change, right, is going to be plus X for the lead, plus 2X for the iodide, right? That, again, doesn't change, right? That stays exactly the same. And so now at the end, we should have X of the lead 2 plus, and then what we should have is 0.010 molarity plus 2X of the iodide in solution. So now that we have that right there, right, we just simply take those values again, and we plug them into the solubility product. So we have KSP is equal to the concentration of lead 2 plus times the concentration of iodide. And so now, right, the concentration of lead 2 plus, we're expecting to be X. The concentration of the iodide, we're expecting to be 0.010 molarity plus 2X. And now that right there gets squared, right? Can't forget the square part, right? That's a very common mistake that people don't think about in those cases. So we have that. And so now what we can do is we just simply, work our way through it. And so what we get is 4x cubed plus 4.0 times 10 to the negative 2x squared plus 1 times 10 to the negative 4x. And that's going to be equal to 1.4 times 10 to the negative 8, right? So that's the KSP value in that case. And so we have those things. And again, now we just simply go through, use our algebra, and we solve for x. And so solving for x, what we get is 1.33 times 10 to the negative 4 moles per liter, right? And that then is the molar solubility of lead iodide in a solution of sodium iodide, right? And so one important thing to think about, right, is that because there are two equivalents of iodide that get dissolved when you dissolve the lead iodide, it actually has a much more a greater impact on the overall solubility, right? If there's some iodide ions already present, right? So we can see right here, just from these examples, that in the case of the lead nitrate, right, that's already a full order of magnitude, right? It's 10 times more in concentration for the lead ion compared to the iodide ion, right, in the sodium iodide case. But in the case of the sodium iodide, right, the solubility is still lower. Right, so even though it's just an order of magnitude less that's initially present for the iodide, it still results in less of the lead iodide being able to dissolve in those cases, and so that's a pretty cool result.